This is Bernard Oyo. Today we are going to discuss photoelectric effect. This is a topic in modern physics that is based on the quantum theory. Now, having mentioned the quantum theory, we are going to look specifically at the photon theory of light, which was postulated by a great physicist known as Albert Einstein. That was the same year when he also introduced the theory of relativity, which is very, very important, and most scientists, most physicists for that matter, already know about the theory of relativity and how it relates gravity to space and time. Very interesting, but we are not going to discuss that today. According to the quantum theory, or the photon theory of light, light is emitted in packets or quanta. Now, each of which contains energy that is given by HF. Okay, let me just try to illustrate that. So we have a packet, and each discrete particle contains energy that is given by HF. So I can just erase what I've written. Sorry. Okay, the eraser, can erase that. And this is what I intended to write. So energy of a photon is given by HF. Okay, I'm just about to give you more information about this. H is known as Planck's constant. So we are going to meet these later on. So I'm just introducing you, but we're going to have a lengthy discussion of H and F. So this is for the photon. And photon is discrete. Now, I will use the analogy of a matchbox and the matchsticks. So the packet is just like that packet of the matchbox. So that is what is called quantum. So quantum, when it is one or singular, we call it quantum. And then plural, now for the packets, we call it quanta. Okay, writing with this a nightmare kind of. So quanta, yes. So that is singular. That is plural for quantum. So this quantum is what I'm relating to the matchbox. And then the matchstick is the photon. So we have the photon. The photon is the matchstick in the matchbox. So that matchstick has energy. The photon has energy. And the energy of the photon is given by E, which is the energy, and then H is a constant known as Planck's constant, named after another great physicist known as Max Planck. Then F is the frequency. Yeah. With that, we can say that all the light comes from the radiating source. So if it's coming from the radiating source, it's just natural that the energy is transmitted as tiny particles, and those tiny particles are the photons. There is a way that we can quantitatively measure the energy of a photon. And in this case, I think a topic like particulate nature of matter will come in handy to help us understand the discrete nature of light, the photon. And these are also areas that Albert Einstein made a remarkable contribution. He had publications on one of the areas, Brownian motion, which is just about particulate nature of matter. So there were major publications that he made at the age of 26 that earned him Nobel Prize later on in his life. Well, let's now move to the quantitative nature of the energy that we talked about. So we can bring in a phenomenon known as photoelectric effect. Yes, just erasing that. So what is this photoelectric effect? Now, photoelectric effect is the process of removing electrons from the surface of a metal by using electromagnetic radiation of sufficient energy. I want you to pay a lot of attention to the details in this definition. So we are talking about electromagnetic radiation, and on top of that, there is sufficient energy. So it's not all the energy that you direct to the surface of a metal can dislodge electrons. So that's why we are talking of radiation with, or rather of sufficient energy. You can have a look at this diagram where we have parallel plates here. So there's plate A, there's plate B, and then we have a galvanometer. We have power supply, positive and negative terminals. Then some radiation, ultraviolet radiation, is directed to plate A. Well, when that happens, that is, when ultraviolet radiations are allowed to fall on this plate A, the galvanometer gives a deflection. So that's the observation that will be made. So how does that happen? As you can see, there is a gap in between. So galvanometer deflects whenever current flows. So if it indeed deflected, then it is a pointer to the fact that current flowed. There was a complete loop whereby the circuit was completed. That is what we are just about to explain, and hopefully you will understand. Now, if you happen to introduce a barrier, that barrier in between here, so that the radiation no longer falls on plate A, then the observation is very clear that the galvanometer will not deflect because you cut off the current. So if there was deflection, there must be something that triggered it. Most likely the radiation, the ultraviolet radiation, did something to the plate A, and then of course it triggered off certain processes that made current to flow. So if you block that radiation, then obviously there will be no deflection on the galvanometer. Yes, so this is it. When ultraviolet radiation energy falls on a metal surface, so the electrons on this metal will absorb the energy, and that what follows is they are removed or dislodged from the surface. Okay, the electrons emitted at plate A are then attracted. So there's plate A, they're then attracted to B. So causing current to flow, hence the galvanometer deflect. There is a point to note, however. Electrons are moving, are dislodged from this surface A, and then there's some potential differences created by the power source, the power supply that we have here. So there's this B is positive with respect to A, and for that matter, the electrons, owing to the negative charge that they possess, will be attracted towards plate B. Conventionally, electrons flow in the opposite direction to current, or conversely, current flows in the opposite direction to that of electrons. So if electrons are moving from A to B, then current will move from B to A. Okay. Yes. Sorry for that. So just want to have a highlighter. So the current will flow in that direction. So that is for current. I'm using a highlighter instead of pen. So let me just get a pen, give me more justice. Okay. Then electrons are moving in that direction. So that is the direction of flow of electrons. So that is the direction of movement of current. So that's our current. Yes. So like that. So it is this current that when it flows through the circuit will make the galvanometer deflect. I hope that is well explained. Let's move to terms that are used in relation to photoelectric effect. The first one is threshold frequency, and we normally use F naught to denote it. I've seen in most cases it's F lowercase and then naught there for threshold frequency, as long as you're doing it in this topic. But that also depends on maybe the book that you're using. Okay, so by definition, threshold frequency is the minimum frequency of the radiation below which no emission of electron occurs from a metal surface. As we saw earlier, the energy of a photon is given by HF. So it's the product of the constant H and the frequency. So if at all, that photon gives energy once upon getting the product of the two, the energy is not meeting the minimum energy requirement for electrons to be dislodged from the surface of a particular metal, then photoelectric emission will not occur. So there has to be sufficient energy, and that sufficient energy is contributed to the only variable here, which is F, because H is a constant. So don't worry, because we're still going to look at H and F, but I've introduced it at the point of talking about the energy of a photon. Another one is threshold wavelength. Threshold wavelength. Now, just like in this formula here, we have E is equal to HF. Now, if that is the case, then it follows that from wave equation, C is equal to F lambda. Yeah, we can make F subject to the formula, and then in this equation, we therefore get C all over lambda. Okay, so for the first case, that was F naught. Yeah, that gives us, okay, we're going to discuss the energy that you get when you multiply H by F naught, the threshold frequency. Then here, as you can see now, lambda, which is the wavelength, is dividing. So for a number that is dividing, if you want to get a bigger quotient, then you have to ensure that it's as low as possible. So lambda should be as low as possible for us to have a greater value of energy. So this should be decreasing so that we get a greater value of energy. So if you your radiation has a higher wavelength, then the energy due to that radiation will be low. And that is the reason why, whereas we were talking of minimum frequency of radiation, below which no photoelectric emission occurs, so here it will be the maximum. So the maximum below which, so we talk of maximum wavelength. So this is the maximum wavelength of the radiation above which, so if you exceed it, then no photoelectric emission will occur from the metal surface. So it is the maximum wavelength of the radiation above which no emission of electron occurs from a metal surface. Then work function that now combines frequency and Planck's constant, or maybe lambda threshold wavelength in this case. Work function. So what is work function? So this is the minimum energy needed to completely remove an electron from the surface of a metal. Just like I said, you don't just have to use radiation that will give any quantity of energy to dislodge electrons. So it must meet a certain minimum requirement. So that minimum energy that you require to dislodge electrons in the surface of a metal is what is known as work function. So work function is often measured in electron volts, just the way it's written here. Electron volts, EV. So E lowercase, as you can see, and then V in uppercase. Yeah, I'm very particular with the symbols that we use in physics because most of them are conventional, and this enables scientists or physicists all over the world to communicate the same language, because when I see a certain symbol, I relate it to a certain physical quantity. Yes. So 1 electron volt is equivalent to 1.6 times 10 raised to negative 19 joules. So if you want to convert from electron volts to joules, then this is the factor that you need to use. So let's now look at the equation. So here we have work function. So this is the work function. Then we have H, we have F naught, which is the frequency. Okay, so the quantities are described here. Work function, that's the W naught. H is the Planck's constant, which is about approximately 6.63 times 10 raised to negative 34 joule second. Now, the symbol for energy is joule, and the symbol is uppercase J. But when you're writing it, strictly write it this way. So the symbol is joule. The symbol is joule in uppercase like that. But now, when you're writing that unit in full, strictly begin with lowercase j, because that is a unit. When you begin with capital J, then it refers to the person. That's now somebody's name, Joe, because most of these units are derived from the people who did a lot of research in certain fields. Yeah, so we have Joule, the person, and then we have Joule, the unit, but the symbol is now uppercase J. I hope you will follow that as a good physicist. Having talked about or described photoelectric effect, having defined threshold frequency, having defined work function and threshold wavelength, it's time for you to apply what you've learned. So the first question, here it is. So an electron is ejected from the surface of a metal with a kinetic energy of 2.24 times 10 raised to negative 19 joules. What is the energy of the electron in electron volts? 1 minute. You can do it. Well, so in this question, what is it that you need to do? So look at the way it is worked out. So that's the answer. So once again, an electron is ejected from the surface of a metal with a kinetic energy. So you're given the kinetic energy, and that is the kinetic energy of the electron. So it's 2.24 times 10 raised to negative 19. You're supposed to convert it to electron volts. We said that 1 electron volt is equal to 1.6 times 10 raised to negative 19 joules. I think that conversion is very easy if you consider what we learned earlier. So we move to the next one. So the second question here, wow, okay. So the second question is, I think, let me just stop something here so you can stop the video. So light of frequency 5.7 times 10 raised to negative 14 hertz is irradiated on a surface of a metal whose work function is 2.6 electron volts. Explain whether photoelectric emission will take place or not. Once again, it's your turn. So here you need to compare work function with the energy of the incoming radiation. So if at all it meets the minimum requirement, then voila, there will be photoelectric emission. If it doesn't, then you know what to say in the answer. So this is how it's worked out. Yes. Okay. So I don't know what happened. Okay, there it is. So the work function is HF naught, and then we're looking for F naught. So we make F naught subject of the formula, which will be work function, this one, over H. Then we have the value of work function, which is given as 2.6 electron volts. So because it is electron volts, we have to convert it to joules. And that means we will multiply it by 1.6 times 10 raised to negative 19. We divide by Planck's constant. So always pay attention to the value of Planck's constant that you're given. So in this case, we are using 6.63 times 10 raised to negative 34. Now, F naught is 6. From this calculation, it's 6.3 times 10 raised to negative 14 hertz. Now, at this point, I think you can explain whether photoelectric emission will take place or not. So will it? No. Photoelectric emission will not take place because the frequency of the light used, look at that, frequency of the light used is 5.7 times 10 raised to 14 hertz, is much lower. Okay, it's lower than the threshold frequency. So the threshold frequency from our calculation is 6.3. So in that case, no photoelectric emission will occur. So thank you very much for your time. And we are going to meet in the next video where we will talk about Einstein's equation of photoelectric emission. Until then, bye.